Hi everyone, welcome to the Probability and Analysis webinar. Today we have Oanh Nguyen from UIUC who's going to tell us about the contact process on random graphs. Let me just remind that the talk is being recorded, but only the active speaker's video is being captured. Oanh, please, the floor is yours.
Yeah, thank you, Thomas, for the introduction, and thank you all the organizers for organizing the event and for inviting me. It's an honor to talk at the webinar. So for the talk today, I would like to talk about the contact process on random graphs, and this is based on some joint papers with Shankar Parmiti at UNC and Danny Nam and Alan Sly at Princeton. Okay, so let me start off by explaining the concept of the contact process. So definition, let G be a graph. And let me start off by an example first. So let G be just a very simple graph with only 3 vertices, 1, 2, and 3. Okay, and the contact process on G is explained in graphical representation. So here is 1, 2, and 3, the vertices again. And at each vertex, there will be a Poisson clock of rate 1. Okay, so I'm going to draw these the Poisson clock at rate 1 at vertex 1, and then there is another independent Poisson clock at rate 1 at vertex 2, and another Poisson clock at rate 1. So these Poisson clocks are points of recovery, which I will explain. Points of recovery. And then for each edge, each direction, like from 1 to 2, there is an edge. So for this direction, there is a Poisson clock of rate lambda, for example, like this. So these are arrow of infection. And also, so this is one Poisson clock of rate lambda. And for direction from 2 to 1, there is also another Poisson clock of rate lambda. So let's say we have 2 times that the clock rings. And similarly, let's say this from 3 to 2 is another Poisson clock at rate lambda. And let's say another one here, maybe, and then 2 to 3 is this. Okay, so these in green are arrows of infection. And here is our contact process given this graphical representation. Let's say we start off with C0, the set of infected vertices. Let's say at the beginning 1 and 3 are infected. Okay, and so if we follow this graph, the first event that we see is this event when we see an arrow in infection. Let's say this is time T0. Actually, because here at time T0, the point 2 send an infection to 1. However, 2 is not infected yet, so nothing really happened. Then the next thing is at time T1 here. When there is a point of recovery, that means that the point 1 being recovered and 3 is the only one infected at this point. And then the next event that happened is at time T2. T2 is when 3 sent in the infection to 2. So the vertices that are infected now are 2 and 3. Okay, and so on and so forth. So that's an example of the contact process. And let me move on to the more precise definition. So let's G is a graph, and CT is the contact process on G with infection rate lambda. If, by definition, if at any state, at any time t, a vertex is either infected or healthy, and CT contains infected vertices, okay? Now, if V is infected at time t, okay, so let's say we have a vertex V, and it has many neighbors, but one of the neighbors is U. Then V is healed at rate 1, meaning so as in the drawing that we saw in the previous page, there is a Poisson clock at rate 1 that whenever the clock rings, the vertex V will be healed. And if V is still infected, it will send an infection to U, to a neighbor U at rate lambda. Yeah. Meaning there are arrows of infections, and these are a Poisson clock at rate lambda. And all of these Poisson clocks are independent. Okay, so that's the definition of the contact process. Are there any questions so far?
So each neighbor of V will get independently infected by.
That's correct.
Okay,
so each
okay.
neighbor of V will get independent Poisson clocks of infection. Okay, so let me talk about some of the results about the contact process. Let me start off with the contact process.
One question. This XIT is these are random numbers, am I right?
CT is random, yes.
But CT contains infected vertices.
So it's a set,
can you explain?
Right? It's a set.
It's a set of vertices. It's
right.
So I should think that some vertices are kind of randomly colored, right? And CT is this colored set of vertices. Am I right?
I didn't hear you very well. So can you say that again, Papa?
So I'm sorry. I'm
maybe look
trying
at
to understand. XIT is the set of infected vertices, right?
Yes.
Okay. Okay. Thank
you. Yeah. Okay. So let's talk about some results, some of the previous results. The contact process on the lattice, the integer lattice. Then Harris in 1974 showed that for the contact process on ZD, there exists a phase transition, meaning there is this threshold lambda C that depends on D, such that when the infection rate is small, meaning it's hard to send the infection, then the contact process starting at all vertices on ZB all vertices infected dies out almost surely. Meaning with probability 1, at some point all the vertices will be healthy and CT becomes empty. Okay. When once CT is empty, no more vertices are infected and the process just stops. Now, if lambda is bigger than lambda C, then the contact process, even if we start with only one vertex, let's say the origin infected, will survive forever with positive probability. Okay. And so that's for the contact process on ZD. If you are interested in learning about the contact process, one resource that I would recommend is section 6 in the book of pre-med, where you can find some very nice results explained very well there. Okay. Now for the contact process on the regulatory TD, there is a very classical result by Pimentel in 1992, who showed that for D is bigger or equals to 3, then there are two thresholds, a two-phase transition here, lambda 1 and lambda 2, well, smaller than strictly small, well, finite, such that if lambda is between 0 and lambda 1, we are in the weak survival, sorry, in the extinction phase. That is the contact process starting at the root infected. Well, what is the root of the tree? Infected to die out. Almost surely. Okay. And if lambda is between lambda 1 and lambda 2, then the same contact process starting at the root infected survives forever. However, the root is infected only finitely many times. Is infected only finitely many times, and we call it weak infection. So this is the, weak survival. And the strong survival is when lambda bigger than lambda 2. In that case, the contact process survives forever with positive probability. So here with positive probability. And rho is infected infinitely many times. And then later you get in 1996 show that this same result holds for D equals 2 in Stacy in 2001 give a simple proof that works for all the greater than or equals to. Now, if we look at these both results, it relies on one important property is that the degrees are regular. So everyone in ZD and in TD, they all have the same degree, and that is an important feature for this work. And moving on to the case when the tree is no longer regular, it becomes significantly more complicated. And so for the model Gaussian tree, for Gaussian tree, would say degree with offspring distribution. Distribution C. Okay, that means at any generation, at any vertex, the number of children of that vertex is distributed as C, and they are all independent. Okay, and so for this Gaussian tree, in our paper, in our first paper with Ramidi, Nam and Sly, and myself, in 2019, we show that if C has an exponential, exponential 2. That is if expectation E to the C is less than infinity for some C larger than 0, then we show that 0 is less than lambda 1, less than equals lambda 2. And that means that there exists the extinction phase. Okay, now previously, prior to our result, there is a theorem by Huang and Duret in 2018, and they show that if C is sub-exponential, which means that for every C greater than 0, the expectation E to the C is infinity. They show that in this case, there is no extinction phase, meaning 0 equals lambda 1, and there is also no weak survival phase. So no extinction phase.
Can I ask one question?
Go ahead, Dr.
At least for those who don't know, what is Galton-Watson tree with offspring distribution Xi? Can you remind us briefly?
Yes, very good question. So, so Galton-Watson tree with offspring distribution C means that we start with a root row, and okay, and we go into sample x1, what is the same distribution as C, and x1 will be the number of children of row, Okay, so row will have x1 children. Now for each child of row, let's say child 1, 2, up to x1. Now for each child, we sample another x2 that is independent of x1. So all of these are independent random variables and they have the same distribution C, and they will tell the number of children that a vertex has.
Okay, thank you.
Thank you, Pata. Are there any questions about these results? So let me recall what lambda 1 and lambda 2 are again. So this lambda 1 is the threshold for the weak for the extinction and the weak survival, meaning if lambda is smaller than lambda 1, then the contact process on the garden blossom tree starting with the root infected will die out with probability 1, and so dies out almost surely. Now, if lambda is greater than lambda 1, then the same contact process starting with the root infected will survive forever. Okay, so that's lambda 1. And lambda 2, if lambda is smaller than lambda 2, then even though the process survives forever, the points that are infected like escapes to infinity, meaning they get further away from rho, and rho is not. Rho is only infected only finitely many times. And if rho lambda is bigger than lambda 2, then the root rho keeps being infected infinitely many times. Now, so that is the result about Galton-Watson trees. Now, there is a close relationship between the contact process on trees and on random graphs. So let me move on now to talk about finite graphs. And so previously I mentioned a result by Pimentel. So we mentioned Pimentel in 1992, who studied the contact process on TD and showed that there are the 0 less than lambda 1 and less than lambda 2 are the phase, the thresholds for the phase transitions. Now, for the finite graphs, in a classical result by Lally and Su, try to find here. In 2017, there is, I should also mention Murray and Ballison. 2016, who studied the contact process on the random regular graph. G and D with degree D, and they show that if lambda is smaller than lambda 1, which is precisely this lambda 1 for the regular tree, then if we start with all vertices at all vertices infected, the contact process will die out in time order log n with high probability. meaning with probability that goes to 1. Okay, as n goes to infinity. And if lambda is larger than lambda 1, then the contact process starting at 1 vertex infected, even just start with 1 vertex infected, then it will still survive until e to the big theta n with positive probability. And the relationship between this this result by Lally and Sue Moret and Vallacy. And Vallacy here with the result by Pimentel is that the regular tree, the random regular, the regular tree is the local weak limit of G and B. Okay. So these are actually very closely related. For our results as well, meaning, so in the previous pages, I explained our result for the Gaussian tree. And that will give us, actually will help us in the study of the contact process on Erdős-Renyi graphs. So contact process on Erdős-Renyi, G and P, where P is D over N and D is larger than 1. Meaning in the case when there is a trying component, and we study the contact process on this Erdős-Renyi graph. Now, it is well known that these Erdős-Renyi as for a fixed D, G in D over N converges in local weak limit to the Gaussian tree with offspring distribution being Poisson with mean D. Okay. So knowing how the contact process behaves, the phase transition of the contact process on the Gaussian tree will help us in the study of the contact process on Erdős-Renyi graphs. And more generally, we study the contact process on G and mu, where mu is the distribution, and this is a random graph where each vertex has distribution mu. So distribution, this is the degree distribution. Okay, and the relationship with the Gaussian tree is that as n goes to infinity, this converges in local weak limit to the Gaussian with distribution mu at the root, and at any of the successor of the root is mu tutor, where mu tutor is a size bias distribution created from mu. Okay. And so what are the results? So what do we know about the contact process on these random graphs? So theorem by again the same set of authors. So we show that there are two thresholds. So in case that mu is exponential, again, it means that expectation of e to the CD is less than infinity, where D is distributed according to mu for some C larger than 0. If mu is exponential, then if lambda is sufficiently small, then the contact process starting on G and mu, and starting at all vertices infected, dies out in time into the 1 plus beta 1. And if lambda is large, the this is with high probability, and the contact process starting at 1 vertex infected, random infected, or survives until time e to the theta n with positive probability. And to prove this kind of result, we also relies on the previous result that I mentioned for the regular for the Garten-Watson tree. And let me take this time to explain, why this time is e to the theta n, why exponential is the correct survival time, and it's a similar result as for regular regular graphs. And so let me explain why it is the case. So if G is a deterministic graph with big O of n edges, then the contact process will survive. Contact process survives. The best that can do is survive until time e to the big O of n at most. And the reason being that at any time, the chance that all of these n vertices are in fact are healed at any time is e to the minus cn for some constant c at any time. And let me explain this after this, but assume.
Sorry,
that,
Anne, are you writing something? Is it just my screen that got frozen? Or?
Oh, yes, I'm sorry. Let me explain again. Thank you so much. I'm writing on this page, but I forget to change it on my screen. Yeah, so here I'm trying to explain. Well, actually, let me right here. So here is a simple proof that I want to give to everyone. So if G is a graph with big O of n edges, then the contact process on G survives for at most e to the big O of n. So this is the best thing that a contact process on G can do. And the proof is that time at any time t, the probability that the contact process dies out. After time t, without sending any further infection. Without sending any further infection. Is greater than e to the minus cn for some constant c. Now, assuming this claim, then at any time, so at any integer time, for example, they will try to heal the contact process. We'll try to heal the contact process, and we know that with this probability, the trial will be successful. So meaning if we try it for e to the 2cn times, at most, at least one time will be successful with high probability. And so it means that the contact process will die out at time e to the 2cn with high probability. Okay, so we only need to see why this claim is true. And why is it true? Let's say that there are, like at this vertex V here, after time t, what is the chance that V is healed before sending any infection? So here V is healed at rate 1, and it's sending infections at rate lambda, and there are dV neighbors of V. Okay, so what is the chance that V is healed before sending any infection? It is 1 over 1 plus lambda dV. Okay. Now, what is the chance that all these vertices are healed before sending any infection? It's the product because they're all independent. So it's a product over V, 1 plus lambda dV, and that is about the product. Let me forget all about all the constant. So it's the product of 1 over dV, which is greater than, by Cauchy swap, is greater than the sum dV over n to the power n, which is greater than e to the minus cn. Okay, so that is a simple, nice proof that I want to mention. And so what else do we know about the contact process on Galton-Watson tree? So in a paper that sorry, my neighbor is it's okay. Sorry, it's noisy on my side. So for the contact process on Galton-Watson tree with distribution C, a theorem in a paper that a follow-up paper by Nam and Sly and myself in 2019. We show that if C has an exponential term e to the CC is less than infinity for some C greater than 0. So in this case, we show that in the previous paper, we show that 0 is less than lambda 1, less than or equals to lambda 2. In this paper, we get the asymptotic of lambda 1 to be 1 over expectation of the random variable C. Okay, so we derive that, and so this is for the Galton-Watson tree, and for the random graphs, G and C, Then we also derive that lambda C minus, which I will define shortly, is also of order 1 over expectation C, and lambda C plus is also 1 over expectation C. Now let me explain what lambda C plus and lambda C minus are. So lambda C minus is the limit as alpha goes to infinity supremum over lambda such that the survival term is great. So this is lambda is 1. Okay, so roughly speaking, this lambda C minus is the threshold for the survival time to be a polynomial, and lambda C plus is the threshold for the survival term to be exponential. So increment percent survival term is larger than e to the beta n. Here equals 1. Okay. And so we derive the asymptotic of these thresholds as well. Okay. Are there any questions?
I just have one question.
Yeah.
For non-experts, if I have random variable xi, how do you model graphs G and xi?
Excellent question. How do I, this graph, right?
Yes, G and xi. How should we think about this?
How should we think about it? Now, by definition, is for each vertex in the graph, so each VI, so you sampled first the degree, so D1 up to DN. So these guys are IID with distribution C. And then, so after you sample the VI, you sample the graph uniformly among all the graphs where vertices sample. G uniformly among graphs where the degree of vertex VI is D. Okay. That's the definition. But there is the configuration model, GNC. And this is the one that is actually more useful, I guess, is that for each vertex, we also sample the degree D1, Dn. And we think about these as half edges. So at V1, there are D1 half edges, and V2, there are D2 and so on. So each of them has the half edges, and then sample a perfect matching of these half edges uniformly at random. Sample a perfect matching. Of the half edges uniformly at random, and you get a graph that is called the configuration model. And there is an important result that the GNC here is contiguous to the configuration model. And what that means is that if you have the probability of this configuration, and C here belongs to some set AN, if this goes to 0, then the same happens for G and C. And probability G and C belongs to AN also converges to 0. Okay. So if you want to prove something what happens with high probability on G and C, then you can pass that to the configuration model and work on the configuration model. Because I have only 4 minutes left, let me talk about some open problems and problems that I'm currently working on. So here, if we look at this page, there are some open problems that we still don't know. So first open problem is, can we show that this one is a strict inequality? So lambda, is it true that lambda 1 is strictly smaller than lambda 2? Meaning, is it true that for Gaussian tree, when the random variable is exponential, has an exponential tail, is it true that there exists a weak survival phase? That's the first open question. Second open question is, for this threshold, lambda c plus and lambda c minus for the random graph, is it true that they are the same? Lambda c plus, is it true that they are the same? And the next question is it true that it's the same as lambda 1 for the Gaussian tree? I should say that this is for the Gaussian of the corresponding distribution. So this is, so these guys are for C. This is the graph with degree distribution C, but in the weak limit is the C tutor, what is the size bias for the Gaussian. So is it true that these are the same and it's the same as the lambda 1 for the Gaussian tree? And one question that I am currently working on with Alan's slide is that in the case when lambda is small, let's say lambda is smaller than lambda c here, we know that the survival time is smaller than polynomial. We want to find exactly what the power is. So when lambda is smaller than lambda c minus, what is the power alpha in the exponent? And so far we think that it's going to be lambda squared, okay? But that is a work on progress. Okay. I guess I will stop here. Thank you very much for paying attention.
Thank you, Anh.
Yeah, thank you, everyone.
Great talk. All right, does anybody have any questions, please?
I have one more question. Juan, you have this condition about exponential tail, that
Yes.
expectation of e to the 6i is finite. Can you explain where does this condition come from? Where does it show up in the
Let me go back to that page.
Why do you require such condition?
Yeah, yes, I think this is the page. So, yeah, also that's actually a good point. So here in the result by Huang and Dirac, they say that some here is actually he established necessary and sufficient condition for the existence phase. If it has an exponential term, then I mean if it's exponential, then it has an extinction phase, and if it's sub-exponential, then it doesn't have an extinction phase. So that's necessary and sufficient. Now back to Papa's question of where does that come from, right?
Yes.
Let me go to a blank page and try to explain that. That's actually a very good, excellent question. Okay, so I'm going to improvise. It's been a long time. I don't recall this before, so I'm just trying to improvise. Pata. Okay, assume that you have a vertex here of high degree. Okay, so it has degree D, which is large. And assume that that here there are, other vertices of high degree. And you have an infection at this point. What is the chance that it could send an infection to these guys of high degree? Now, if it's very likely for a vertex of high degree to send an infection to another vertex of high degree, then you can repeat this process and show that your contact process will survive for a long time. Okay? So now if you have if your the offspring distribution C is sub-exponential, then it's very likely that if you go to a constant, so L is a constant depth in the tree, then it's very likely that you find many vertices of high degree. If it's sub-exponential, you find many, and it's also with exponential probability that you send an infection directly from here to here. So if it's L is a constant, then there is a chance. What is the chance that here is rho, for example, and here is a vertex of distance L away from rho? What is the chance that rho send this infection from here to here without being healed? Meaning at any step, what is the chance that rho send this infection to this guy before being healed? That is lambda over 1 plus lambda. And if we repeat that L times, then rho will successfully send an infection to this guy. So that is lambda over 1 plus lambda to the power L, which is about e to the minus CL. Okay, and if with this probability, you can find many guys here. So if here you can find e to the 2CL vertices of large degrees. Okay, so if there are many vertices of large degree and each of them, the chance that rho successfully sends in the infection to each of them is larger than e to the minus CL, then with high probability, one of them will be, actually many of them will be infected. And then you can run that argument, repeat that argument, and that will show that your process will survive on the tree like forever. Now, if C, so that is when C is sub-exponential. Now, if C is exponential, then you cannot, find that many vertices here. And so it's hard for you to pass the infection to successors.